Okay, gonna make this one quick. We're looking at transitioning now from vectors in 2-space to 3-space, so from 2D to 3D. I'll use 3-space and 3D interchangeably, just so you know. If we look at, this is an example of a diagram in 3-space. You can see a little bit here, the x-axis kind of coming out. It's drawn at an angle, but we'll sort of see why in a second. The y-axis now goes across left to right. The z-axis goes up and down. So the box is actually drawn around this figure where this represents our axes. And this one, with this big circle in the middle, this is our x-axis. It's coming straight out at me or straight into the page. If we rotate it, we can sort of see there, that's the axis itself. And that was just the tip of the arrow on the axis. But basically, we think of it in terms of this is our axis with the x coming straight out. We tend to draw it though so that we can actually see the numbers. I'm going to close that up. I don't know how well that showed up, but we'll sort of see it better maybe here. So the key concepts moving forward, the first key concept I'd say, and it's not written in here, is that absolutely nothing changes. We have a third dimension, that's it. So there's going to be a third number in all of our calculations, there's going to be a third number in all of our thought processes, but nothing else changes. So looking at this super quickly, if I have a point here, -1, -3, 4, it means that I've dropped basically 1 into my page or into the desk, gone 3 to the left and 4 up to determine where that dot is. If I have a vector, again, now this is actually a bit poorly drawn in that it's a vector to the point. Ideally, this would have been marked up with square brackets, but the same idea holds true. If I'm drawing a vector to that point, out 2, over 3, up 5, and so you can sort of visualize it that way. Now, as I said, we're going to keep stressing the fact that nothing really changes going from 2 dimensions to 3 dimensions. So if we do have a point, it will be written in round brackets with 3 values, the first of which is x, meaning the in and out, sort of the off the page into your desk, the y value being the left right, and the z value being the up down. If it is a vector, this is sort of suggesting right here, if it's a vector, there'll be square brackets indicated exactly the same way. So as it was before, square bracket around 3, 4, 5 means it's a vector. Round brackets around 3, 4, 5 means it's the actual point in space 3, 4, 5. Unit vectors, again, don't use them very often other than if they happen to, if we see them, we can convert to the Cartesian vectors because they're nicer to work with. But the concept remains. There is a unit vector we call I. It goes 1 in the x direction and 0 in the other 2. J goes 1 in the y direction and 0 in the other 2. And k now is the third. Surprise, I, j, then k to represent x, y's, and z's. K goes 1 in the z direction and 0 in the others. Let's see, any Cartesian vector can be written this way. Sure, it can be written as a combination of the other ones. That's fine as well. Again, we tend not to do this because it's just, at this point, not really very valuable. Magnitude is the one that you might be surprised at, although it does make sense. When we looked at magnitude of a 2-dimensional vector, we looked at the x and we looked at the y and realized they formed a right angle triangle. And so we used a Pythagorean theorem, or a variation of the Pythagorean theorem. Added the x value, multiplied the x value by itself, so squared it, squared the other one, add them together, and take the square root. Now there's a third value involved, so the magnitude is exactly the same. The first value squared plus the second value squared plus the third value squared, added them all up, and take the square root, determines my magnitude. Other things, vector addition, before we would add the 2 first values to represent our first value, our new first value. We'd add up the 2 second values to represent our new second value. What a surprise, we now add the 2 third values to determine our third value. Multiplying by a single scalar value, so as we did before, if we want to double the size of a Cartesian vector, we double every value. We multiply each of the values by 2. There again happens to be a third, but nothing else changes. So all the logic from 2 dimensions is exactly the same in 3 dimensions. There's absolutely nothing new as of today. Subtraction, obviously same as well. And then the last couple of things, or this one is just talking about how you determine a vector if you have 2 points. And as we did before, we recognized the vector is the amount we moved in the left-right direction, and the amount we move in the up-down direction to get from the one point to the other. Now, of course, it's the amount we move in the z direction as well. So find the difference between the two x values, find the difference between the two y's, find the difference between the two z's. That is now our new value, exactly as you'd expect it to be. And then this is just kind of a magnitude formula talking about if you only have the points, but you recognize maybe that x2 minus x1 is now the value from our vector. So it's really just kind of combining the magnitude formula right up here with the fact that we're determining our vector values from 2 points. And then finally, dot product. The basic formula for dot product, just trying to get that to disappear. The basic formula for dot product, the u dot v equals, doesn't change. It's the size of the one vector times the size of the other times cosine of the angle between. Now again, the cosine of the angle between is what's going to take the portion of the u vector that is in the v direction and bring it so we can actually multiply it. So if u is 100 newtons, for example, but only half of that is in the x direction, maybe we have cosine of 60, then this times cosine gets me the 50 that is in the direction of v. We multiply that by the size of v to determine what the multiplication would be. The second formula for dot product is just multiply the two first terms and multiply the two second terms. And now, of course, we will add the two third terms multiplied as well. Okay, so really just trying to stress absolutely nothing new today, except there is a third number in everything we do. And please hold on to that. Visualize it if you can. Your vector is now kind of heading back towards you sometimes, or into your desk, or into the space in front of you. But otherwise, everything is exactly as it was.